In this screencast, we're going to use a simulation to help explain how to read ternary phase diagrams that you'll see in problems where you have three components that may or may not be miscible with each other. This does come up a lot when you're doing liquid-liquid extraction type of work. If you go to this website, you'll pull up the following simulation. You'll see here we have component A, that's green, component B in blue, and component C in the dark red. There's two main ways that we can interpret these diagrams. When you see these, typically the compositions are going to be reported on the axes, such that as you move towards that component, you're going to get to 100% of that component. So one way to think about this is if this apex for component A is 100% component A, if we're at that point, then we draw a line down, and at the other end, the line between B and C, we have 0%. So any lines perpendicular to the line I've just drawn are going to be our reading lines for component A. So as you can see, the point we're at right now, if we go across following one of those lines, that is going to give us a reading for component A. In this case, we're at 0.31, which you can see up here in the simulation. Following the same logic for 100% component C, we draw a line downwards from C to get to the line between A and B where we have 0% on that line. And now any lines perpendicular to this line are going to give us our readings. So if we do that, you can see the dashed line that takes us to 0.38 shown here. So try this with component B. Draw a line away from component B's apex. We get to 0% B on the line between component A and component C, and any lines perpendicular to this are going to give us our readings. So you can see that going this way, we get a reading of 0.32 for our mass fraction of B. So you could play around with the simulation to test yourself and also see how things change. So as I drag this dot within the diagram, I'm changing the composition between our three components. Of course, this does imply that all three components are miscible since we have a single phase with this composition. So let's pick a point where we have an equal mass fraction of A, B, and C. As you expect, this would fall right in the middle of this triangle. So we have about 33% of A, B, and C. In this case, to make it 100%, we have 0.34 mass fraction of A. So if we wanted to be 100% A, we would be on that apex. If we want to be 100% C, we would be at this apex, and so forth. So if I was dead center at the bottom here, again, reading this way, we get 0.43 mass fraction of B. Reading this way, we get 0.10 mass fraction of A. And we could either calculate the difference or read off the third axis and see that we have 0.47 mass fraction of C. So this is one way to read these ternary diagrams. An alternate way to read them is the following. Starting with component A, we know that the apex up here is 100% A, or a mass fraction of 1, and at the bottom is 0. So anywhere in between is going to give us a distance upwards to component A, and that distance, or that fraction of the total, is our mass fraction of A. Which one way to interpret it is if we have a line that goes from the bottom to the top, and that's equal to 1, then this distance from the bottom to the point is 0.29 of that full distance. So again, for component C, we go to the other line, we draw a straight line, and the distance from that base to the point is a fraction of the whole. In this case, it's 0.39, so we have 39% of C on a mass basis, or a mass fraction of 0.39. We do this for B, and this fraction from the base to the point is 31% of the whole, or a mass fraction of 0.31. So sometimes you'll see the actual numbers within the triangle, and so this is one way to interpret the composition at any given point if you're looking at that diagram. So let's say we had a mass fraction of C of 0.2. If we want to keep that, we move parallel to that base. And what has to change as we increase A is that our mass fraction of B must decrease, as we see in the simulation. Same thing goes on for A. If we have 50% A, we have to move horizontally to maintain that 50% A. And what changes is the amount of B and C. So hopefully this gives you an idea on how to read these phase diagrams. Do go to the simulation and play around with it. It will definitely help. Thanks.